Welcome to VFD Vibes, your place for all things related to variable frequency drives. If you're interested in how to make things turn, or manufacturing technology in general, then this is the place for you. I'm your host, Greg Weichman, and this is episode 6, Calling All Agents. If you listened to the last episode, then you know Tony and I had recorded more than we could fit into one episode. Luckily, the content was split almost in half between startup tips and information on troubleshooting some of the most common drive fault codes. This is where we are going to pick up today. Don't worry, you won't be lost if you missed episode 5, Sturdy Startup, though personally, I still think it's worth a listen. We finished the last discussion talking about the built-in monitors in our drives and how you can use them to monitor the status of any input or output. In startup, this is very useful to make sure you have both a run command and speed reference, otherwise your motor will not turn. Assuming we have verified both of these requirements, what if we are still not able to get the drive to run? What if we have faults keeping us from running or tripping soon after we start running?
Yeah, let's use a scenario. Let's say your colleague installed a drive 3 weeks ago, and 3 weeks has gone by. You think everything's fine. The customer calls up and says, hey, so-and-so put this drive in, and every morning we come in, it's faulted out, and we've realized when we turn power off and cycle power, then it turns back on and it runs for the day. But we're tired of doing this. Can you guys come out here and fix this? So now you're out there working on this. You're in front of this drive and it's running, but it's been faulted every morning. You ask the people on site, well, what was the fault? I don't know. It's just the light is solid red and it's sitting there not working. We just turned the power on and off. Now you got to figure out what fault is there. Well, we have additional monitors in the U3 group, which will show you the last 10 faults, and they are date and time stamped, which is pretty handy information to know to see exactly when it's happening. Now, let's say in this case, it was an overvoltage fault. You went into U301, you see OV for overvoltage, very common fault, probably the most common fault you'll troubleshoot if you spend any time working on VFDs. Now, we also have in the U2 monitor group what we call a fault trace. What that is several metrics. It's a snapshot of exactly what happened on the last fault at the time of fault. And if you know how to interpret that data, it's going to make troubleshooting that overvoltage fault much easier. And I'll give you an example. If your fault trace history told you that your output frequency was 52 hertz, your frequency reference was 20 hertz, so we know we're slowing down to 20 hertz. Maybe our motor amperage was very low for running at 52 hertz. So we know we're lightly loaded. And let's say our bus voltage was 815 volts, which is substantially higher than where it normally would be in a typical application of maybe 650 or maybe 680 volts DC. So we know we're decelling. Our bus voltage is ramping up. We probably could assume we were running at 60 hertz. We got down to 52. The bus voltage hit 820 on a 400 volt class drive. And then we tripped out on this overvoltage fault, and now it's sitting there idle, and they come in the morning and reset power, and it ramps up and it's fine. Now you could look at your fault trace, your U3 group, you'll see all your overvoltage faults the last 10 times. And let's say it's happening at 5 o'clock every day. Well, maybe the signal generator or speed control, however it's configured, is running at 60 hertz. And the process shuts down, we go to a minimum of, let's say, 20 hertz, what would probably be the proper thing to adjust? Well, if we're getting it on a decel time, you'd probably want to extend your deceleration rate. The factory setting is 30 seconds. And as I mentioned earlier, I always recommended extending those XL and decel times. Yep. That would be a perfect example of avoiding a regen situation where we're regenning power and putting it back into the DC bus.
So if I understand it, we have 2 fault histories, I'll call them. Well, one we actually call a fault history, and that is a log of the last 10 faults that have occurred. And then what we call the fault trace is a snapshot of a bunch of drive variables or monitors at the time of the last fault.
Yes.
And the intention of that is to help you find the root cause of the fault, because there are probably a half a dozen reasons you could have an overvoltage fault. It could be on the input side, the output side, due to regen conditions, decel times. So without this other information to determine what was going on, was I trying to accelerate the drive? Was I trying to slow it? What was the input voltage doing at that time? It could be a pretty big wild goose chase if you don't have something to help point you in the right direction. And that's built into all of our drives, so that is a pretty cool feature. You've already hit on overvoltage as one of the top faults that you've heard in tech support. What are some of the other big ones out there?
Yeah, probably OL2, a drive overload where we're exceeding the rated output current of the drive. That could be a big variation of causes. One of the big ones was probably the low impedance, high efficiency motors in HVAC applications. Now I'm talking Z1000 and now HV600, our current flagship HVAC drive. If you connect that drive to that low impedance motor, sometimes the predefined V by F pattern, what do I mean by V by F? I mean volts per frequency pattern, because we're sending out a fixed voltage across the 60 hertz range. And on a variable torque application, which would be for a fan or pump, versus a constant torque application, let's say a conveyor, where we need a linear voltage that goes up and gives half voltage at half speed. On a variable torque application, we're going to drop that voltage at a part speed. Maybe it's 100 volts at 30 hertz and then 460 at 60 hertz, because we don't need full torque on a fan or pump. If we give it full torque, we're probably oversaturating the windings and overloading the drive. And in that case, if we're sending too much voltage at a part speed and oversaturating the windings, kind of feeds back into the drive. And if you run into this situation, it's going to pronounce itself as high amperage at a part speed. So you're going to ramp up, amperage is going to look pretty normal, and then you're going to get a pretty high spike at maybe 25 or 30 hertz, and it might fault out the drive. If that were to happen, one of the things you'd want to do is adjust the V by F pattern and lower the voltage at a midpoint. And one of the recommendations I always use for tech support for this situation was E103, E is echo 103 equals 6 or 7, and retest and see how it works. All that was another predefined pattern that moved those voltage points around, and sometimes that solved your problem.
So again, when we talk about optimizing the drive efficiency for the application, that V by F pattern is, well, one, we're avoiding a fault condition, but we're actually, once again, optimizing to get the most efficiency for the application that we're running.
Yeah, most torque per amp.
Great. What about drive overcurrent situations?
Yeah, that's another one that you might see. That's a more severe fault. If you had high amperage instantaneously, think phase to phase short or phase to ground short on the output side. And I have a kind of a funny example of this, and I'll talk about it now. It was during my time in tech support, and it was an OEM air handler that had one of our micro drives installed in it. And I get the call, and he says, everything's normal. Amperage is normal. I get up to 45 hertz or around 45 hertz, and I get an OC fault. And right off the bat, I'm thinking that's kind of weird, because OC is, like I said, a significant fault, and it usually happens right on start. When you hit the start button, you have that high current spike and it faults out. But in this case, he's running up to 45 hertz. I had him disconnect the motor, and this would be an excellent test to perform in this situation if you had a OC on startup, or an SC or a GF, ground fault, or a short circuit overcurrent OC. Disconnect the motor from the drive and ramp the drive up. If the drive ramps up to 60 hertz with the motor disconnected, I would probably bet $100 every time that there's nothing wrong with that drive. And now you have to look at the motor cabling or the motor itself, maybe run a meg test. You could almost look at the drive as a high-tech megometer, because it's going to be able to detect a short circuit if you have weak insulation or a short on the output wiring. Well, this case, we reconnect the motor. He gets up to 45 hertz. Again, it faults out just like before. And I ask him, did you look at the motor cabling? Maybe pull the cover off the motor, make sure everything was sound in there, no wire nuts came off. No, I haven't looked at it. It goes through a bulkhead fitting into another chamber. And I ask him, well, can you take the door off? If it only takes you a minute, I'll hold on the phone. Yeah, sure. So he puts the phone down there, and I hear him taking the door off. About 30 seconds goes by, and I hear, "Oh, you got to be kidding me." And he gets back on the phone. He's like, "You're never going to believe it. The motor cables are draped across the motor pulley, and all the insulation's worn off, and there's bare copper, and it's touching the motor pulley when it gets up to speed." And that's a perfect example of how an overcurrent is generated, a short to ground or a phase to phase short. In that case, he had to repair that motor cabling. But the important takeaway from here is pulling those motor leads off the drive and retesting it. If it ramps up to 60, look at your motor, make sure your wiring's intact, because if you condemn that drive without doing a thorough test or investigation trying to find out what's going on, you're going to condemn that drive, either put it to the side or maybe send it back for warranty, get a new drive. You're going to put that new drive in there, and what do you think is going to happen if he didn't find the problem? The same exact thing. If he had changed that drive, he would have got OC at 45 hertz. And it happens very often where we get drives returned into tech support with no problems found. That is something that happens quite often.
To me, that's more frustrating than finding the problem with the wiring
Well,
itself.
that and your colleagues are not ever going to let you live that down, and your customer is not going to be very happy.
What I'm really hearing is that the problem is rarely ever the Yaskawa VFD.
Jokingly,
joke,
yes, yeah. But that is jokingly, I would agree with you. And as I said, it's as a tech support engineer, it was my job to convince you that the problem was outside the drive, because very often the call started out, "My drive's not working, I need a new drive." And again, I would convince you that it was external to the drive.
And quality will be a discussion for another podcast episode, but I do think it is really unique and cool that 100% of Yaskawa drives are tested off the manufacturing line. They are physically wired to a motor and spin a motor, and it is that essence of quality that coming to work here I've really seen, and I think as to why our entire tech support team can be so confident in this ability that it's often not our drive. And
Yeah.
that is something I can hear in the way that you talk about it, the way that you're proud of the company and the products that
Yes.
we do produce.
Absolutely. Yeah.
We've hit a lot of great troubleshooting topics. Any other that are high on the list?
I'll talk about input phase loss because I want to mention how it's detected. I think it's important to mention this. And I think we touched on this a little earlier in the other podcast, the basic VFD function, but we'll hit on it here because it would be good from a technical point to understand it. You might think that the VFD has a voltage monitor on the front end. That's not the case. The Yaskawa VFD or HV600, some of the other drives like Z1000 and such, monitor the DC bus, and they monitor the voltage on the DC bus and what we call DC bus ripple. If you have three-phase applied to the input power of the drive, we're running a three-phase motor, probably everything's running normal and there's no issue. If you were to lose an input phase, and now you're single-phasing that drive with 2 wires in and 3 wires out, and you might think, how does that happen? Well, it can happen if you have a poor connection, let's say. Poor connection will degrade over time because if we're passing current through it, we're generating heat, and a poor connection will get hotter, and that heat degrades the connection even more to the point that eventually it's going to fail and you're not going to be able to pass current through it. In that situation, we're now missing an AC wave coming in, one of the 3 waves, and there's a gap in the charge that's applied to the DC bus. And if we're running that motor at speed, we're pulling a lot of power from that DC bus. With that missing phase, we now have a fluctuation in voltage that goes outside of an acceptable range. And that generates an input phase loss fault. The drive monitors that bus ripple, and if it exceeds a limit to protect the capacitors from failing, we fault out. Now, it's important to know that that input phase loss fault can also be generated from an output condition, and we'll touch on that now so you understand how the drive works and detects the circuit. Let's say you have a cooling tower up on a roof, and it's old, it's been up there 20 years, and it always had some vibration, and now finally one of the fan blades has fractured or fallen off, it's sitting in the basin, and This is now up there. It's completely unbalanced and it's really womping away as it's accelerating. And you're there to troubleshoot it. And this drive is maybe in a mechanical room and the cooling tower is 100 feet away on the roof. So you don't know what's going on up there. You don't hear it shaking away. And every time you start this up, maybe you get to 20, 25 hertz and it faults out on input phase loss. Well, how would you troubleshoot an input phase loss fault? I would probably start with an amp probe, an amp clamp, and measure the input amperage. If we had a low leg, we'd find it right away if we had that poor connection. But if we have an input phase loss generated from an output condition, you're not going to see a low leg. You're going to have even amperage draw on the input side, and you're going to probably be scratching your head. What's going on here? This shouldn't be happening. Well, it can happen because we have the output transistors on the output side of the drive that generally put power out to the motor, but you can think of the output side as a two-way street. We put power out, but we can also take power back in a regen situation. With that out of balance fan, and let's say this cooling tower has a diameter of 6, 7, 8 feet, it's a large fan, we're getting into a situation where half of the rotation might be being overhauled because it's on a downward spin maybe, the heavy side of the fan, and then it's lightly loaded, and then it's loaded again where we're driving it, and that oscillation is taking power from the DC bus, but on the unbalanced part of the rotation, maybe it's being overdriven, and it's now generating power and it's putting power back on the DC bus. And what does that do to our bus level? It creates a fluctuation. And as it speeds up, that fluctuation, that DC bus ripple exceeds that limit, you're going to generate an input phase loss fault. And that's why either an input or output condition could create an input phase loss fault.
Yeah, who would have thought that you would have to check the output side of the drive to find a fault labeled for the input? That's why it's so critical to know how the drive determines that fault, is because it's really measuring the voltage on the DC bus, which is the middle of the three sections of the drive. And both the front and the back end of the drives have the ability to affect that bus. One is your incoming, as you mentioned, but also how the load is pulling power out. So that's great deduction. That's great troubleshooting to be able to figure out. And that should hopefully really help some listeners that might come across this and be baffled as why there's nothing wrong with the input, but they're getting a fault that says input in the name of it.
Right. And these procedures and aspects of our drives, the Yaskawa drives, probably apply to many other manufacturers, and how that DC bus ripple is monitored. That's probably the case for other manufacturers too. If you understand this, you can understand how all drives kind of function.
Hopefully you've been able to glean that our tech support has seen a lot of this, and the drives have the tools to help you figure out what's going on. Some problems are easy, some are clear, some can get a little bit complicated. And this is why Yaskawa offers world-class tech support. 24/7/365, meaning it could be Christmas Day or a holiday or a government holiday, and we will still have someone answer the phone and get back to you. The tech support department is another topic I plan to elaborate on in another episode, how we achieve that standing of world class. But for all our listeners, we want you to know that it is just a call away. 1-800-YASKAWA. It's always available to help. You can hear the expertise that Tony has, and that is expertise that our entire tech support group has. The last thing I'm going to ask you, Tony, is when people do call in, what are the first things that tech support is going to ask from them?
Yeah, probably you're going to want to make sure that you have the model and serial number for sure. The fault code is definitely going to help, and the modified parameters. And what do I mean by that? Each Yaskawa drive has a menu that shows the modified parameters, anything that's been changed from factory default. So if your drive is not running, or it's doing something it's not supposed to do, or it's not doing something it's supposed to be doing, you can give that set of modified constants or modified parameters to your tech support engineer, and they're going to help figure out exactly what's going on. Usually from a list of modified parameters, I could probably tell you in about 30 seconds why it's doing what it's doing.
And when you say model number, we've mentioned we have our standalone drives. We also have package drives. Now, in a package drive, there is a standalone drive on the inside. So when you say model number, which is it that they need?
Good point. Yeah. So if it's a cube drive or a standalone drive, you're going to have the model and serial number of that drive. And the serial number of a drive only will start with 1W. That means that it was built in Buffalo Grove, Illinois. But a package solution, a drive with a package like a bypass or a circuit breaker or some other options, will have its own packaged model number, and it's going to have a serial number that starts with 4W, and that indicates that it was built in Oak Creek, Wisconsin. Tech support is going to want the packaged model and serial number if you're working on, let's say, a configured cabinet or a bypass cabinet.
Tony, it's awesome that our Yaskawa customers have this tech support at their hand, but what would be some other options if they want to increase their own level of understanding, their own expertise with our products?
Oh, sure. Yaskawa offers a bunch of different training for all the different product lines, whether it's in class here at Waukegan, Illinois at headquarters, or even at your local distributor. We do a teaching program called the Roadshow, where it's a quick 8-hour class, and we would do that for different industrial lines. What we talked about today really is just scratching the surface of a handful of faults and sequencing and run command speed reference to the drive. There's really so much more that exists that we just don't have the time to talk about. Some of those training classes, if you were to come in at HQ headquarters, would be maybe 3 days. Hands-on troubleshooting, programming applications and such.
Yeah, those are 3 big topics in our training: installation and startup, programming applications, and hands-on troubleshooting. If you go to our training website at training.yaskawa.com, you can find all kinds of information on this, including the different formats we have for our classes. We have in-person classes in which you come to our facility, roadshow classes in which we can go to a distributor or customer site, e-learning, which is self-paced online, and virtual courses where we can ship out demos and the students interact with an instructor virtually in real time. So if you want to increase your knowledge of the product or how to best program it for specific applications, whether it be fan, pump, HVAC, industrial, irrigation, constant torque, etc., check out what we can offer. With teams of application experts such as Tony, these courses really are able to bring in real-world experience which can help you in your own personal applications. That's enough of a plug for training, as I plan to bring a full episode on the topic in the future. And that's going to do it for this episode, Calling All Agents. Hopefully this breakdown gives you a clearer path when you're up against those tricky fault codes. With the right steps and a little patience, most issues can be tracked down and resolved. When you need a little assistance, gather your drive and fault information and give our best-in-class technical support a call. Any time of any day, they'll be able to help get things moving. If you enjoyed today's episode, please like or follow this podcast to stay informed of when new episodes launch. And if we're doing a great job, please leave us a 5-star review. Thanks for joining us, and as always, we'll see you next time on VFD Vibes.